Okay, so electrolysis, the notes. And then we'll do some questions as well, just to get used to the topic. Okay. Alright, so what do you know about electrolysis? To start off with, like, have you done this at school?
Yeah.
Do you know what it is? What are you trying to do here? What's the goal?
We use electricity to separate two metals.
Not two metals, but yeah, you're right. You use electricity to separate an ionic compound. So something like, aluminium oxide. So you start with aluminium oxide. This is because aluminium is reactive, so in nature, when you find aluminium, it's already reacted with oxygen. So you don't find pure aluminium in nature, because if you have it outside, it will just react with oxygen. So when we look for aluminium, we find aluminium oxide in the ground. So then we have to kind of turn that into aluminium and oxygen. And this process of taking a compound and breaking it down to aluminium and oxygen, to do this, we need to do electrolysis. So this method here is electrolysis. So it's reversing an ionic equation, ionic reaction. So, for example, sodium reacts with chlorine to make sodium chloride. This would happen naturally, because in sodium chloride, these would exist as ions, which are more stable. Right? So if you want to undo this process, you want to take sodium chloride and turn it back into sodium and chlorine, you'd have to use electrolysis. Okay. So we don't have to do, so the goal is to extract the metal, is to kind of start with a compound and get the metal out of there. Right? We want the aluminium. So we only need this for metals more reactive than carbon. So if you look at the reactivity series, you'd have potassium, sodium, lithium, calcium, magnesium, and then you have carbon, aluminium, and then carbon, and then zinc, iron. A few more metals here, but we just need to know about zinc and iron, and then we have hydrogen, and then copper, silver, gold. Okay. So metals that are less reactive than carbon, all of these metals here, we can simply reduce with carbon. So for example, if I have, this is because metals can do displacement reactions. For example, if I had iron oxide or iron sulfate, FeSO4, and I react that with magnesium, Mg, because magnesium is more reactive than the magnesium can displace the iron. You can kick the iron out and take the sulfate. So that would make turn my mouse controls on so I can scroll sideways. Okay, well, it's not working for some reason. Anyway, let's just keep moving. So the magnesium would be able to take the sulfate away. And so you get magnesium sulfate, and you get iron. So if you want to extract iron, we can do it this way. We can just react with something more reactive than itself, right? Because something more reactive than iron will be able to displace the iron, and you get the iron from its compound, and you get the pure iron created. So we would use, for this purpose, we would use carbon. So when you find iron in the ground, you would find it as iron oxide, Fe2O3. So what we do is because iron is down here and carbon is up here, we can react with carbon. So we add that to carbon, and then the carbon would displace the iron. So the carbon would take the oxygen, you'd get carbon dioxide, and you'd make iron. So anything less reactive than carbon can just react with carbon. Right? So anything in this part of the table, we can just react with carbon. Carbon would displace the metal, and you can create the metal that way. But of course, carbon can't displace anything more reactive than itself. So carbon can't be used to extract any of these metals. So if you have aluminium oxide, reacting with carbon wouldn't work because carbon can't displace it because carbon is less reactive than aluminium. So for metals like this, we would need to use electrolysis. Okay, so when you're trying to extract potassium, sodium, lithium, calcium, magnesium, that's when you have to use electrolysis. So electrolysis would undo the chemical bonds. So it would split the aluminium oxide into aluminium ions and oxygen ions, oxide ions, and then it would turn the aluminium ions into aluminium metal, and it would turn the oxide ions into oxygen gas. Okay, so it sort of undoes the chemical equation. the chemical reaction. Okay, so that's the purpose. It's to extract metals that we can't extract using reduction. Okay, so let's sort of analyze the process. So let's say we have molten sodium chloride. Okay, let's see what let's say. All right, so process of electrolysis. So when an electric current is passed through molten ionic compounds, the compound decomposes or breaks down. This process also occurs for aqueous solutions of ionic compounds. So if you mix the ionic compound into water, then this process also occurs. Liquids and solutions that are able to conduct electricity are called electrolytes. So we need to use electrolysis, we need to have an electrolyte. We need a liquid that can conduct electricity. Covalent compounds cannot conduct electricity, hence they do not undergo electrolysis. An electrolysis cell is an name given to a setup used in electrolysis, which consists of the following. So you have electrodes, which is a rod of metal or graphite through which current flows into the electrolyte. The electrolyte is the ionic compound in molten or dissolved solution that conducts electricity. The anode is a positive electrode, the cathode is the negative electrode. The anion is the negative charged ion, which is attracted to the anode. And the cation is the positive charged ion, which is attracted to the anode. So this is what a cell looks like. So the cell would have a power source, positive side, negative side. That would be connected to the electrodes. The electrodes would be something unreactive, usually something like platinum. The platinum is expensive, so sometimes they just use graphite, because graphite conducts electricity and is very cheap. So in the extraction of aluminium from aluminium oxide, you use graphite. Okay, and then you have the tank. So to make electricity flow, we need to complete the circuit. We need like something so the charge can go in the loop. Right, so to do that, we use an electrolyte. So electrolyte is a compound it's a liquid that can conduct electricity. So this would be, in this case, molten sodium chloride. So you take sodium chloride. So we'll study the electrolysis of molten sodium chloride. Okay. So you take sodium chloride and you break it down into sodium ions. So you melt it, basically. When you melt an ionic compound, the ionic compound is solid, looks like this. It has a giant ionic lattice. And when you melt it, the ions break apart, right? So the ions become free to move. So when you have a ionic compound, which is molten or in solution, you have these positive ions and negative ions, and these ions can flow. And because ions can flow, it can conduct electricity. So you can complete the circuit. Yeah. So you get molten NaCl. So you take the NaCl, you melt it, and that will give you sodium ions, and that will give you chloride ions in the solution. Does that make sense? You're muted.
Yeah.
Yeah, okay. So we have these ions now. So once we power the battery up, this side is positive, this side is negative. What that would do is it would take electrons from this side, it would pull the electrons out, and then push them onto this other side. So over time, the electrons build up on this side, so this side becomes negative. And over time, we have a lack of electrons on this side. We have more protons than electrons. Protons can't move. Right? Protons are stuck inside the nucleus. So that side is left with a positive charge. Okay, so you build up separation of charges. So this is called the anode, and this is called the cathode. Okay, so the ions are attracted to the opposite charge because of electrostatic attraction. So the sodium ions get attracted to the cathode, and the chloride ions get attracted to the anode. Okay. At the anode, what happens is that the electron of the chloride is pulled into the anode and then pushed onto the sodium on the other side. Okay, because this side is positive, it will pull the electron out, and then the battery or the cell will then push that electron onto the sodium on the other side. So in this process, the chloride ion would lose its electron. So the chloride ion would lose the extra electron it has, turn into a chlorine atom and that extra electron. So this is at the anode. And at the cathode, this sodium ion that you have here would gain that extra electron and turn into sodium atom. When you're making chlorine atoms, if you make two chlorine atoms next to each other, those will join together to make a chlorine molecule. So you'll be making chlorine molecules instead. So to balance this, you have to say, put a 2 there, put a 2 there. So that's what's happening. At the anode, you're making chlorine gas. So you'll see, at the anode, you'll see bubbles of chlorine gas coming off. Right? And then at cathode, you're making sodium metal. So over time, you'll start to see sodium sort of building up around the cathode. You see like a metal sort of forming around the cathode. So you take the sodium chloride, you break it down, you melt it, so you get sodium ions and chloride ions. Then you use electricity to separate the ions out. You take the electrons away from the chloride ions and give them to the sodium ions. So the chloride ions become chlorine gas, and the sodium atoms become sodium metal. So you sort of turn them, make them go from ions back to being atoms. And that's electrolysis. Does that process make sense? I can repeat it if you want me to. But
Could you just repeat the last part?
okay, the equations.
Yeah.
Okay, let's just do the whole thing again. So we start off with a cell, and we connect the cell to two sort of metal electrodes. Right. And then to complete the circuit, we need to kind of connect these two together through a conducting substance. So we use a molten ionic compound. So in this case, we want to do electrolysis of sodium chloride. So what we do is we melt it. And when we melt the sodium chloride, the ions become free, because it's an ionic compound that's made of ions. So the sodium chloride melts down into sodium ions and chloride ions. Right? So you're going to have sodium ions and chloride ions freely moving around here. And because these are freely moving charged particles, they can conduct electricity. So you complete a circuit. Okay, so now electricity starts to flow. As electricity flows, because one side is positive, one side is negative, the positive side will attract electrons off from the metal, and the battery will push those electrons onto this side. So over time, you build up a positive charge here, and you build up a negative charge on the other side. Okay, so that is called the anode, and that is called the cathode. The positive is the anode, the negative is the cathode. So the ions are then attracted to the opposite charges, because that's how electrostatic forces work, opposites attract. So the sodium ions go to the cathode where it's negative, and the chloride ions go to the anode where it's positive. The chloride ions have an extra electron, so once they go to the anode, because of the positive charge, the anode will take that extra electron, and just like the electrons before it, that extra electron is then pushed onto the cathode, where the cathode is negative, so it'll repel the electron and it'll push it onto the sodium. So the circuit is used to transfer this extra electron chlorine has onto the sodium. Okay, so the chloride ion, you start with so the chloride ion would lose this electron. So you start with the chloride ion, and you end up with a chlorine atom and an extra electron. And this extra electron gets transferred away. So you're making chlorine atoms here. And once you make two chlorine atoms, these two chlorine atoms will join together to make a chlorine molecule, because they're more stable as a molecule. Right, so you make Cl2 here. So to balance this, you can say two chloride ions make one chlorine molecule and two electrons. Okay, and then these electrons would then be transferred to the other side. So on the other side, the sodium ions will gain those electrons, and that will. So now, once the sodium ions are missing an electron, so once they gain the electron, they go back to being sodium metal, sodium atoms. So on this side, you make chlorine gas. On the anode, you make chlorine gas. You make bubbles of chlorine. You can see those coming off. And on the other side, you make sodium metal. Right. So you're going to start to see metallic sodium start to form around the cathode. Okay. So that's electrolysis.
Yeah.
Alright, so this is how it works. You have the electrolytic solution. Once you turn the circuit on, the ions move to opposite charges, and then the electrons get transferred from the negative side onto the positive side. So this side would lose the electrons, this side would gain electrons. So the negative ions become atoms, and the positive ions also become atoms. And you end up with atoms as your elemental. So these are atoms now, no longer ions. So you take an ionic compound and turn it into element, and turn it back into its elements. That's what's happening. Okay, so here's an example of molten lead to bromide. So first thing you do is you melt it. Okay, so once you melt the lead to bromide, you make lead 2 ions, and you make bromide ions. Then they'll go to opposite charges. So the lead ions go to the cathode, and the bromide ions go to the anode. So at the cathode, the lead ions are attracted to the cathode, where they gain electrons. So each lead ion gains 2 electrons at the cathode, forming metallic lead, and at the anode, each bromine ion loses 1 electron, and then 2 bromine ions are needed to form 1 bromine molecule. So 2 bromine ions will each lose an electron, and then these 2 atoms will then join together to make a bromine molecule, so Br2. So what you'll see is bubbles of gas coming up from the anode, bromine gas, You'll see solid metal lead forming at the anode, at the cathode. Okay, so at the anode you make bromine gas, at the cathode you make lead metal. Alright, so that brings us to the extraction of aluminium. So we discussed this earlier, anything more reactive than carbon is over there. So anything less reactive than carbon we can extract with heating with carbon. Right, so carbon will displace the metal from its compound. Silver, gold usually found as pure elements, so we don't have to react anything with this. Anything more reactive than carbon though, we have to use electrolysis. Okay. So aluminium is one of those metals, which if you want to extract it, we have to use electrolysis. So aluminium you typically find in the ground as bauxite, which is aluminium oxide. Okay, so first thing we do is we first purify the bauxite to produce aluminium oxide. Bauxite is like a mixture of different stuff. So we purify it and get the aluminium oxide out. And then we dissolve it into molten cryolite. So cryolite is this, so bauxite by its, aluminium oxide by itself has a very high melting point. But cryolite has a lower melting point. So if you dissolve it into molten cryolite, we can lower the melting point. We can lower the temperature needed to dissolve to kind of melt the aluminium oxide. So this is because aluminium oxide has a melting point of over 2000 degrees Celsius, which would use a lot of energy and be very expensive. The mixture with, if we mix it into molten cryolite, the mixture has a lower melting point without interfering with the reaction. So we do that to melt this more easily. And then the reacting mixture is put into an electrolysis cell made from steel lined with graphite. The graphite lining acts as the negative electrode, with several large graphite blocks acting as positive electrode. Okay, so this is what the diagram looks like. So rather than having the two electrodes like that, now what we do instead is we have this electrode sort of go all the way around. Okay, so the negative electrode is now sort of on the bottom, like that, all the way around. And then the positive electrode is sort of up here. Okay, so and you can have like multiple, like you can have multiple connections there. So that's connected to the positive side of the battery, and that's connected to the negative side of the battery. And then we fill this with the mixture, with bauxite dissolved into cryolite. So in this mixture, you have aluminium ions, Al3+ ions, and oxide ions, O2- ions. So the oxide ions are negative; they go to the positive electrode, the anode, where it turns into oxygen gas. The gas is dissolved out, and the aluminium ions go to the negative electrode, where it turns into aluminium metal. And because of the high temperatures, you'll get liquid aluminium metal here. So molten aluminium, which you can then sort of pipe off. Okay. So at the positive electrode, you get oxygen, and the electrodes are made of graphite. If you remember, graphite is just carbon. So graphite is just made of carbon. So if you make oxygen and you have high temperatures because you have to melt the aluminum oxide, then the carbon and oxygen will react with each other and make carbon dioxide. So over time, these electrodes get used up. The carbon on them gets used up by the oxygen. So this is why these electrodes need to be replaced. So the carbon in the graphite anode reacts with the oxygen produced to produce carbon dioxide. This results in, as a result, the anode wears away and has to be replaced regularly. So a lot of electricity is required, so it's a major expense. This is why aluminium is expensive. Okay. So that's the reaction. So at the anode is positive electrode. So what we do is you start with aluminium oxide. You dissolve it into cryolite at high temperatures. That will dissolve the aluminium. So it will turn into aluminium ions and oxide ions. At the anode, the positive electrode, you're going to get the negative. That negative ion will go there. So the oxide ion goes there, and it loses 2 electrons to become an oxygen atom. And then when you have 2 oxygen atoms next to each other, they'll join together to make an oxygen molecule. So you can balance that. So you can say 2 oxygen ions, oxide ions, lose 4 electrons to give you 2 atoms which join together to make an oxygen molecule. And at the negative cathode, so these electrons that the oxygen is producing at the anode would then be transferred onto the aluminium at the cathode. Right? So at the cathode, your aluminium ions would gain electrons and turn into aluminium metal. Okay, so you're going to over time build up aluminium metal at the down here. Does that make sense? Any questions?
No.
No? Okay. So these are the half equations. All right. So now let's discuss what happens. So far everything is molten, right? So molten means you melt it and you just, so if you have lead bromide, PbBr2, and you melt it, you just make lead ions and bromide ions, which is nice and simple. So we'll go back to our example with sodium chloride, NaCl. So sodium chloride, if you melt it, you make sodium ions and you make chloride ions. Okay. However, sodium ions can also be dissolved, right? So if I take sodium chloride can also be dissolved, and I add it to water, then that also breaks down into ions. So if you dissolve the sodium chloride in water, it also makes sodium ions, and it also makes chloride ions. But in addition, the water also ionizes. So the H2O that you have also turns into H plus and OH minus because of the ionic compound. So the water also ionizes and turns into, and you have additional H plus ions and OH minus ions. Okay. So now if you try to do the electrolysis, you have two ions at each end. So for aqueous sodium chloride, you have sodium ions and you have chloride ions, but you also have hydrogen ions and you also have hydroxide ions. So what happens is that they would go to opposite terminals. So the positive ions would go to the negative side and the negative ions would go to the positive side. But now they will discharge preferentially. So there's a difference in reactivity between them. So one will react before the other does. Okay. So at the cathode, remember what's happening. So the cathode reduction is happening. Okay. Reduction is gain of electrons. If you remember your oil rig mnemonic, reduction is gain of electrons. So if you look up here at the cathode, the aluminum ions gain electrons to become aluminum metals. So reduction is happening. Okay, so that's reduction. Whereas at the anode, you're losing electrons. So that's oxidation. Because oxidation is loss of electrons. So this list of metals that we have, this is based on, so if you go up, it gets more reactive. And metals react by losing electrons. So as you go up, it's better at losing electrons. Okay, because metals react by losing electrons, they become positive ions to react. Which means that as you go down, they become better at gaining electrons. So as you go up, they are better at losing electrons, they're more reactive, but therefore as you go down, they become better at gaining electrons. Or they become better at getting reduced. So in our example, we had hydrogen ions and we had sodium ions. Hydrogen is better at getting reduced than sodium is. Okay, so hydrogen is better at gaining electrons.
Yeah.
It's the opposite of the reactivity series. So since we have a competition here between the hydrogen and the sodium, diagram. So here at the cathode, we have hydrogen ions and we have sodium ions. They will compete with each other to say which one is to kind of gain electrons. Hydrogen is better than sodium. So hydrogen would get reduced. And once all the hydrogen is gone, only then can sodium start getting reduced. Like even if sodium gains an electron, hydrogen will just take it from sodium. Right? So sodium is only discharged after the hydrogen is discharged. So at the cathode, the hydrogen ions will gain electrons to make hydrogen atoms, and then two hydrogen atoms will join together to make a hydrogen molecule. So you'll have this reaction happening. So over here, you'll start to see hydrogen gas being produced. Okay, and on the other side, you have the anode. At the anode, oxidation is happening. And halogens are better at being oxidized than anything else. So the rule for the anode is halogens. If a halogen is present, it is oxidized. Otherwise, hydroxide is oxidized. Okay. On the other side, over here, the rule is if copper, silver, or gold is present, they get reduced. Otherwise, hydrogen gets reduced. Because these are the only three things less reactive than hydrogen. So these are the only three things better at gaining electrons than hydrogen. So if copper, silver, gold is present, they get reduced. Otherwise, hydrogen is reduced. So here we don't have copper, silver, or gold. We have sodium. So hydrogen is reduced. Okay. Whereas here we do have a halogen. Right? If a halogen is present, it's oxidized. Otherwise, hydroxide is oxidized. So here we have on the anode we have chloride and we have hydroxide. So because we do have a chloride, that's what's going to get oxidized. So the chloride ions would lose their electrons to make chlorine atoms. To make chlorine atoms, and then they'll make chlorine molecules. So you get this. So at the cathode, anode, you're going to make chlorine gas. Okay. So now you have to pick between the ions. You're going to have two ions on each end. You have to kind of decide which one gets reduced and which one gets oxidized first. That's the idea. So an aqueous solution will always contain water molecules. In the electrolysis of aqueous solutions, the water molecules dissociate, producing hydrogen and hydroxide ions as well. So these ions are involved in the electrolytic process, and their chemistry must be considered. Okay, so which ion gets discharged at which electrode depends on the reactivity of the elements involved. All right. So this was the working example. So here's a working example. So we have predicted products formed at each electrode in the electrolysis of magnesium iodide. Okay, so we have magnesium iodide solution. So when we do electrolysis on this, the magnesium iodide will split up into magnesium atoms, iodine ions, iodide ions, but also the water, because the solution has water in it. The water will split up into hydrogen ions and hydroxide ions. Okay, so between these two, the hydrogen gets reduced because copper, silver, or gold is not present. Between these two, the iodide gets oxidized because halogen is present. Halogen means group 7. So if chlorine, bromine, iodine, astatine, if these are present, fluorine, if these are present, then they get oxidized. Otherwise, hydroxide gets oxidized. So in this example, the hydrogen and the iodide gas gets oxidized. Okay. So hydrogen is discharged at the cathode as it's less reactive than magnesium, and then iodine is discharged at the anode as iodide ions are present. So anytime if a halide is present, then the corresponding halogen is formed. Otherwise, oxygen is formed. So otherwise, the hydroxide gets reduced. For example, here we have copper sulfate solution. So copper sulfate, CuSO4. If you dissolve this, aqueous, so the ions present are copper ions, hydrogen ions, sulfate ions, and hydroxide ions. Right? So the rule said that if copper, silver, or gold are present, they would get reduced. So there is copper, so the copper gets reduced, not the hydrogen. And then the rule said if a halide ion is present, they get oxidized. There is no halide ion. So in this case, the hydroxide is what's going to get oxidized. So at the cathode, the copper ions will gain electrons. They'll be reduced to copper metal. And at the anode, the hydroxide ions would lose their electrons to make water and oxygen gas. Okay, so to balance this, I have to put a 4 here, a 4 here, a 2 here, and a 2 there. Actually, no, a 2 there, and that's fine. That's balanced. So you make oxygen gas. The water you make just stays as water. So what you're going to see is oxygen gas being made. So now at the cathode you make copper metal. At the anode you make oxygen gas because the hydroxide gets oxidized. Okay. So copper is discharged at the cathode as it's less reactive than hydrogen, and then if a halide is present, then the corresponding halogen is formed. Otherwise, oxygen is formed. So in this case, the halide, oxygen is discharged at the anode, as no halide ions are present. So that's the rules. Okay, that's fine. So we also have to understand half equations. So we've done sort of half equations so far. So at the anode, so at the cathode, there you go. So in the electrolysis of lead to bromide, the half equation of the negative electrode, the cathode is this. So the cathode is negative, which means it has lots of electrons, so it'll donate electrons. So when the lead ions go to the cathode, the lead ions will gain electrons to make lead metal. Whereas at the anode, the negative ions go to the anode, and the negative ions have electrons. So you can say that the bromide ions lose an electron to make bromine atom, right? So you can then move this losing an electron to the other side, and then that becomes the bromide ion makes a bromine atom and an extra electron. Okay, so both of these are fine. And then the idea is you have two of them making a bromine molecule. Alright, so you have to understand the half equations. Here's some examples. Right. Okay.
Yeah.
Okay. So, so notice here that when the nonmetal is a halide, so chloride, chloride, then at the cathode you always make chlorine, you always make the halogen. When the negative ion is a sulfate, basically not a halogen, then at the negative ion you make oxygen. At the negative electrode you make oxygen instead, right? Because the hydroxide is what's getting discharged, getting oxidized. On the other side, anytime you have copper, the copper is what's going to get produced. If you don't have copper, you make hydrogen. Doesn't matter what, you can have sodium, you can have lithium, doesn't matter. You make hydrogen instead. So you have to understand why that happens. Okay? Okay, so let's do questions. Alright, so aluminium is extracted from its ore by electrolysis. The electrolyte is a mixture of molten aluminium oxide and cryolite. What is the role of cryolite? So what does cryolite do? Why do we use it?
To lower the melting point.
Yep, good. This question is about the electrolysis of zinc chloride. So it's molten zinc chloride. So when you see molten, it means it's, we melt it. In other words, there's no water. Right? So you don't have to worry about hydrogen ions and hydroxide ions. You just have two ions. You just have the zinc ions and you have the chloride ions. That's it. When it's molten, you just have two ions. So one of them goes to the anode, the other one goes to the cathode, and that's it. Right? So why do we need molten zinc? Why can electrolysis not be performed using the apparatus shown here where they have solid zinc chloride? So you can say a solid ionic compound cannot conduct electricity. And since they cannot conduct electricity, we don't have a complete circuit. So the electrons can't sort of flow from one side to another, which is why we can't do electrolysis. So we need to melt it. Chloride ions move towards a positive electrode. Explain why chloride ions move towards a positive electrode. You can say because they have opposite charges, with chloride ions have a negative charge, because they don't say that in the question, so I'm trying to point that out. Because then it's 2 marks. You can't just say because they're attractive. You're going to explain why they're attractive. Because chloride ions have a negative charge, and opposite charges attract. Okay. So the chloride ion moves towards the positive electrode. Name the product formed at the negative electrode. So if I do electrolysis of molten zinc chloride, what's formed at the negative electrode? Think it
Is
through.
it zinc solid?
Yeah, zinc solid. Good. So solid zinc. Or just zinc is fine as well. So explain the type of reaction that occurs at the negative electrode. So at the negative electrode, the zinc ions will go there. So that's Zn2+, and because the negative electrode has lots of electrons, the zinc ions will gain some of those electrons to make zinc metal. So the ion will lose its charge because it gained the missing electrons. Right? So currently it's the positive ion because it's missing electrons. It has more protons than electrons, that's why it's a positive charge. So if I give those electrons back, it'll just go back to linear metal, the atom. The type of reaction here is reduction. The explanation is that the zinc ion is gaining electrons. If you remember the mnemonic oil rig, oxidation is the loss of electrons and reduction is the gain of electrons. So in this case, because our reactant is gaining electrons, it's a reduction reaction. One of the products from the electrolysis of zinc chloride is chlorine. The balance the half equation is shown here. So we've done this before, it's just a 2 here and a 2 here. So 2 chloride ions would lose 1 electron each to make 2 chlorine atoms, which will join together to make a chlorine molecule. And you have these two spare electrons, which would then get transferred to the lead. So those electrons over here would then get pushed onto the lead on the other side. Okay. So you're making electrons which then get transferred onto the other metal. Okay, so this question is about the extraction of metals. The method that is used to extract metals can be determined by the position of the metal in the reactivity series. So you have some metals shown here. So the least reactive go down here, the most reactive go up here. So draw a ring around the correct answer. So displacement by carbon is used to extract what? So which of these is extracted by displacing with carbon? So we'd have to react it with carbon, and carbon can kick the metal out.
Iron.
Yep, iron. So calcium is more reactive than carbon. So calcium can't displace carbon. Carbon can't displace calcium. Platinum you just find as a pure metal. So even though platinum is less reactive than carbon, you don't actually have to extract it. You just find it as a pure metal. Iron is the one you'd have to displace with carbon. And then electrolysis is used to extract which of these?
Platinum.
No, like I said, platinum is just pure metal. You don't have to extract it.
Oh.
Platinum is the least reactive thing here, right? You're going to just find that in the ground as a pure. It's not going to react with anything. It's very unreactive. So there's no need to extract it.
There's a calcium.
It's calcium, yeah. Because calcium is more reactive than carbon, so we can't extract it using carbon. Right? So we can only use electrolysis on it. So calcium you would find in the ground as calcium oxide. So how do I get rid of the oxide? Well, I can't react with carbon. So I'd use electrolysis to split the ions up and produce calcium. Okay. So aluminium is extracted from aluminium oxide using electrolysis as shown. So you've got the carbon electrodes, one side's positive, one side's negative, and then you've got the molten cryolite aluminum oxide, which makes the ions. So the oxygen ions go to the positive side, the aluminum ions go down here, where they're reduced into aluminum atoms, and these atoms would then flow out, because of the high temperatures it'll be a liquid. Whereas the oxide ions go over here, they turn into gas, which then get removed. So what's the chemical formula of aluminum oxide? So these are the ions, Al3+ and O2-. So to form a compound, we have to balance the charges. So to do that, we need 2 aluminum ions, which will then have a charge of +6, and we need 3 oxide ions, which will also have a charge of -6. So now that the charges are balanced, so the compound would be Al2O3. 2 aluminiums, 3 oxides. Make sense?
Yeah.
Aluminum oxide is mixed with cryolite. Why is aluminum oxide mixed with cryolite? It's because so options are to make more aluminium. No. To increase the melting point. Why would we want to do that? That's bad, right? That makes it harder for us to keep it liquid. So it's to decrease the melting point, so it's easier for us to melt it. What's produced at the positive electrode? So at the positive electrode, what do you get?
Positive. The oxygen.
Yep, oxygen. Good. And you could also say carbon dioxide, because remember, because this is made of carbon, and you make oxygen here at high temperatures, these two might just react together and make carbon dioxide. So you could also get away by saying carbon dioxide, but what you're going to make first is oxygen, and then the oxygen might further react to make carbon dioxide. But yeah, oxygen is what you the electrolysis is producing oxygen, and then that might react some more. So the positive carbon electrode has to be replaced periodically, explain why the positive carbon electron needs to be replaced. So the positive carbon electron needs to be replaced because you can say the oxygen that is produced will react with the carbon under high temperatures. Under the high temperatures. Because remember, to keep this molten, we need the high temperatures. Decrease carbon dioxide. So the electrodes will wear down. Or the electrodes. Electrodes are worn away over time. So the equation is that carbon reacts with oxygen to make carbon dioxide. Complete the half equation. So what do we have here for the formation of aluminium?
Electron.
Yeah, how many?
3.
3. There you go. Alright, so this question is about electrolysis. A student investigates the electrolysis of different salt solutions using equipment. So what observations would be made if a metal is produced at one of the electrodes? So if a metal is produced, what would we see? What do you think?
The positive one.
Think about it. Metal ions are positive. Like if you have magnesium ion is positive, so where would it go?
To the negative.
To the negative. So you'd make the metal at the negative electrode. That's the first thing you'd see. So observation 1 would be yeah. So I would appear at the negative electrode. And then the second one, you can say, the properties of metals is that they're shiny, or lustrous. So you can say that a shiny compound would be seen. Okay, so let me just look up the exact wording that they want. Okay, so what would you see? You can say color change at the electrode. You can say mass increase at the electrode. Because over time, if the metal builds up in the electrode would either would build up like that, so the mass would increase. Because the metal sort of builds up on top of it. Also, the color would change because the metal might be a different color from the electrode. The electrode might be like silver, and the metal might be gold, so you could see a color change. Also, the salt solution might change color because salt solutions often have color. Like copper sulfate solution is blue. All right. So over time, as the copper ions get removed from the solution, the blue color would fade away. All right. So you might also see a color change in the salt solution because the metal ions create the color, and as you use up the metal ions, turn them into solid, the color would change. Which electrode will non-metal ions such as chloride and sulfate be attracted to? So that's the positive one. If they say why, you'd say also because opposite charges attract. Okay. So an aqueous solution of copper 2 chloride is electrolyzed. Which of the ions is not present?
H minus.
H minus, good. And that's not a real thing. And then the student investigates the electrolysis of copper 2 chloride and sodium sulfate solution. So here, crucially, they have solutions, which means water is mixed in. Okay. So it's not molten, it's a solution. So always kind of look for that word, whether it's molten or it's in solution. So table 1 shows the reactivity series. So the question is saying, what product is formed? So this is what we're electrolyzing, copper salt chloride solution, sodium sulfate solution. What do we make at the cathode? What do we make at the anode? Take your time. Think it through. You can write things down if you want to, if you think it helps. So start off by splitting up into the ions. So copper to chloride solution. So you make copper ions, chloride ions, and then from the solution you make hydrogen ions and hydroxide ions, right? So the ions you're going to have are copper, chloride, H plus, OH minus, right? So where would the positive ions go? To the cathode or the anode?
Cathode.
Yep. So the positive ions go to the cathode. So at the cathode you have copper and you have hydroxide, and then at the anode you have the chloride and you have the copper and hydrogen. Here have the chloride and the hydroxide, and then now one of them would be preferentially discharged. So between copper and hydrogen, which one gets discharged? Which one is reduced? So the less reactive one would get reduced. So now look here. Because the more reactive ones are better at losing electrons, the less reactive ones are better at gaining electrons, right? And at the
Copper.
cathode you gain electrons, so copper is better at gaining electrons. So copper is what's going to get produced there. And on the other side, we say that if there's a halide present, halide ion, that's what's going to get produced. Right? So if there's chloride, we just make chlorine. Right? So we can say the less reactive here is copper, so copper gets produced. And if there's a halide, we just produce the halide. If there's not a halide, we produce hydroxide. So on this side, we're going to make copper metal. On this side, we're going to make chlorine gas. Okay, that's basically what you have to say. So can you try the second one by yourself? So what do we make here?
So at the cathode there's hydrogen.
Yep, good.
Then at the anode, sulfate.
No. So if there's a halide, we produce the halide. Right, but there's no halide here, it's just sulfate. So between the sulfate and the hydroxide, we're going to produce hydroxide. Right? If I had like a chloride or a bromide or an iodide or a fluoride or an astatine or an astatine, whatever, if I had any of these are all halides, right? So if I had any of these, I produce the corresponding halogen. So if I have bromide, I produce bromine. If I have iodide, I produce iodine. If I don't have these, I just produce oxygen. So if I don't have any of these, then it's the hydroxide that's going to get oxidized. And when I oxidize hydroxide, it makes oxygen. So I just produce oxygen. Make sense?
Yeah.
Yeah. So here we had a halide, so we make halogen. But here we don't, so we don't do that. Yeah. So this question is about the extraction of aluminium using electrolysis. The process is displayed here. So we've got the positive electrodes, and we've got the negative electrodes. So you can imagine that's connected to the positive terminal of your battery, of your power source, and that's connected to the negative terminal of your battery. Right, something like that. So the electrons can go in here, and the electrons are then pushed onto the aluminium over here. Okay, so that's like how the electrons are moved from one ion to another. Anyway, so you have molten aluminium here, produced. So you start with molten aluminium oxide dissolved in molten cryolite. So you have your mixture here, and then from the mixture you produce oxygen gas, and you produce aluminium metal down here. Okay, so these are positive, and that's negative, and then so the aluminium goes to the negative and creates this molten aluminium down there. So why isn't aluminium extracted by heating with carbon? So the reason is aluminium is more reactive than carbon. so a carbon cannot displace it from its compound. Does that make sense? Yeah.
Yeah.
Okay, and explain why aluminum is formed at the cathode. So how would you word that? How would you word the reason aluminum is produced there? Because I know you know conceptually why it's produced, but how would you sort of word a 3-mark answer?
Because
So start off with the
they
charge. So what charge do aluminum ions have?
positive.
Yep, so you can start off by saying aluminium ions have a positive charge. Positive charge. And as a result of that, what happens? So they go to the cathode, right?
Yeah.
Yep. So they move to the cathode, move to the negative electrode, and then at the negative electrode they gain electrons. So the aluminium ions gain electrons and become aluminium metal, aluminium atoms. That's the idea, which is why aluminium is produced at the cathode. So aluminium ions are positive, so they go to the cathode, and at the cathode there's excess electrons, and the electrons get pushed onto the aluminium ions, which are then reduced and become aluminium metal. Explain why carbon dioxide is formed at the anode, and why the anode must be continuously replaced. So you can say oxide ions are oxidized to produce oxygen gas at the anode. Okay, and due to the high temperatures, this oxygen gas will react with the carbon in the electrodes, because the electrodes are made of carbon, so the electrodes are worn away and must be replaced periodically. So every now and again you have to replace them. Okay, so oxygen gas will react with the carbon in the electrodes and produce carbon dioxide. Yeah, what about this? What's the answer here? What do you think?
Because cryolite.
Yep, so why do we use the cryolite? Why do we use a mixture?
Because it lowers the boiling melting point.
Yep. So why do we use a mixture? You can say the aluminium oxide is dissolved in cryolite. And okay, there's music. I'm hearing music. Okay, turn the music off. Anyway, okay. So the aluminum oxide is dissolved in cryolite. The resulting mixture has a lower melting point. So what's the benefit of that? Why bother doing that?
Because it's dangerous if it's
Not really.
high.
Not really. No one's going to go near it. Like even with the lower melting point, it's still pretty hot. Like this is still like 1,000 degrees, right? But pure aluminum is like 2,000. Pure aluminum oxide is like 2,000 degrees. So what's the benefit of getting it down from 2,000 degrees to 1,000 degrees? So it's the costs. So costs less, less energy is needed to maintain the liquid state. Because we need it to be liquid, otherwise it wouldn't conduct electricity. So to maintain the liquid state, we need high temperatures. So by lowering the melting point, we need less energy. So you can say, so the process is cheaper. All right. Okay, so over here we have, this question is about electrolysis. This one investigated the electrolysis of copper chromate. So chromate ions are yellow. So on one side you have copper ions, on the other side you have chromate ions, CrO4 2-. Explain the color of the chromate ion solution, copper chromate solution. So copper ions are blue, chromate ions are yellow. So you'd say the copper chromate would be green. So copper ions are blue, and chromate is yellow. So you'll see a mixture of blue and yellow, which is green. So the solution would be green. Make sense?
Yeah.
So here, explain why the negative electrode increases in mass. So you take the copper chromate solution. So you have copper ions, you have chromate ions, you have hydroxide ions, you have hydrogen ions. So on the negative electrode, you're going to have the copper and the hydrogen. On this side, you're going to have these two. And then preferentially, copper is less reactive than hydrogen, so you're going to discharge copper here. And then if you don't have a halide, you discharge hydroxide. Okay, so on this side, you make oxygen gas. On this side, you make copper metal, which builds up around the electrode. So on the electrode, the copper ions gain electrons, and you make copper metal. So you start to make copper metal. Okay, so why does the negative electrode increase in mass? Because copper ions are reduced, and copper metal builds up on the ion. Alright, so for homework, I'll give you some homework this lesson.
Yeah.
Do this. This is quite basic, just a way of revising everything. And then you can try the medium questions. So, okay, alright, so I'll see you next time. Take care.
Yes.